Welcome to the world of sapphires. Valuable, unmatched beauty, rarity and purity are the ultimate qualities of this precious gemstone. Virtually unscratchable, sapphires are the only natural material on Earth as hard as diamonds. In nature, sapphires are formed from high-purity alumina deep in the Earth's crust. Like any naturally occurring gemstone, heat, energy and pressure over millions of years stimulates the growth of these natural sapphire crystals. Today, mankind has the technology to recreate the formation of sapphires using high-purity alumina under intense pressure and heat. The formation takes place in high-tech furnaces where large single sapphire crystals are grown from high-quality alumina. From these crystals, sapphire wafers and sapphire glass are extracted using diamond cutting technology. These synthetic sapphires, like the natural sapphire gemstones, are highly valuable and prized. Today, synthetic sapphire is playing a large and growing part in our everyday modern lives. Sapphire wafers are used in the manufacture of cost-effective, energy-efficient LED lights. LEDs, the lighting of the future, offer huge energy savings and are rapidly replacing traditional light globes around the world today. Semiconductors in our electronic devices, phosphor-plasma televisions and scratch-proof watches are some of the many applications that belong to the sapphire family. Smartphone manufacturers are already making the exciting transition to the unscratchable sapphire display screens. We all look forward to a sapphire future of unscratchable glass. To meet this sapphire future, Altech Chemicals, an Australian company, is aiming to be the world's leading supplier of high-purity alumina. Altech has rapidly grown to consolidate its strategic advantage through the rapid development of its kaolin mine in Western Australia and its proposed high-purity alumina chemical facility in Johor, Malaysia. The company's proposed state-of-the-art production facility will produce high-purity alumina specifically designed for the synthetic sapphire market. Well positioned in the Asia-Pacific region, customers around the world will trust the quality and reliability of Altech's high-purity alumina products. Altech's proposed expert customer support and state-of-the-art packaging and distribution service will be second to none. Altech Chemicals is aiming to be the leading supplier of the key ingredient for sapphire glass, high-quality pure alumina. Altech Chemicals, meeting a sapphire future.
Good morning, everyone, and thank you for the opportunity to tell you the Altech story. So our vision is to be the world-leading producer of high-purity alumina. And just as it says in the video, alumina forms sapphire. A bit like carbon forms diamond, alumina forms sapphire. And as it says, the hardness of sapphire is 9 on the Mohs hardness scale. Diamond is a perfect 10. So the only thing that will scratch sapphire is actually diamonds. Now the thing is that the colour of the sapphire, the blue colour, is actually from impurities in the alumina that create the colour. So iron and chromium creates the blue in the sapphire. Now today, if you want to make synthetic sapphire for your watch face, you don't actually want a blue tinge on your watch face. So you need to start with high purity alumina. So we start with 99.99% purity. We call that 4N purity. Now, how does that compare to the smelter grade alumina that Alcoa produces down south? Well, that's about 99.5%. It looks pretty pure anyway, but unfortunately there's about 5,000 parts per million of impurities, which is mainly sodium, because they use sodium hydroxide as part of the Bayer process. Now the problem with sodium is that it gets locked into the crystal structure, it's very difficult to remove, and is a big problem for the electronics industry. The price of our material is worth $27,000 a ton. And this is typical of high purity materials like silicon, graphite, and so on. So The normal alumina is worth $400 a tonne. 3 nines is worth $6,000 a tonne. 4 nines is worth $27,000 a tonne. So it's a high value, high margin material. Now, the way they make synthetic sapphire, as they show in the video, they buy high purity alumina, they put it into a furnace, they heat it up to 2,000 degrees, nearly as hot as the sun. Alumina melts, and then they let it cool over 21 days, and it slowly grows a single crystal of sapphire. And that's what it looks like looks like a big ice block. But unfortunately, fortunately, it's nearly as hard as diamond. So they core it out using diamond cores, and then they slice it up to make sapphire wafers. And the sapphire wafer is the building blocks of the LED industry. So an LED is a light-emitting diode. It's actually a semiconductor. So like the semiconductors on in your laptops, an LED is a semiconductor. So in order to make an LED, you start with a substrate. You put some chemicals on it, some electronics, and more chemicals, and that sandwich is a semiconductor. And what they found out with these semiconductors is when they put electricity to it, it creates light. So light photons is created. Now, the beauty of the LED industry is that 90% of your energy to an LED produces light, whereas in the conventional globe, 90% of your energy is wasted as heat. So really, LEDs is the lighting of the future, and you can see that adoption in vehicles, domestic lighting, concert lightings, and so on. The other application of high-purity alumina is in the lithium battery industry. So you heard of the Samsung battery fires. When a battery starts to overheat, what actually catches the light is the plastic separator. So there is a plastic separator that keeps the positive and the negative electrodes from touching each other. And when a battery overheats, these separators catch a light because it's plastic. So now these separators have to be fire retardant. They're spraying high purity alumina across the separators and even on the cathode and anode. So this is another big area of demand. The other applications is obviously on your smartphone. So at the moment, your camera lens on your iPhone is sapphire glass, and some manufacturers have gone to full sapphire glass screens. Now, another interesting point, you see some of these old-style globes in pubs. They look like vintage globes. Why are they building such inefficient globes? They're actually LEDs. So if you look at the filaments, they're actually tiny LEDs. So very actually efficient lighting. This is what I mentioned about some of the phones. Huawei, Cryocora, HTC have gone to full sapphire screens on there. So the question is, how hard is this sapphire material? Well, this is the watch face of the Apple Watch, but I think most people would have watches that have sapphire glass on it. This is a very complicated scratch test. So gentlemen, when you get home, try that. Put a drill through your watch, and if you actually go through and you start bleeding, then you don't have sapphire glass. All right, the whole demand in the world is 25,000, so it's not a big demand. This is a classic lithium story 8 years ago. This is the demand. You can see very similar in the electronic sector, driving lots of growth. It's expected to climb to 86,000 tonnes per annum by 2024, something like a 40,000 tonnes per annum growth. We're only putting on 4,500 tonnes. The growth is at 17%, and it's all driven in the LED sector and the lithium battery sector. So that's the growth curve. But even if we looked in the lithium battery side, it would require 4 times our plant just to service the lithium battery sector going forward. 70% of the material is used in the Asia-Pacific region, because that's where you expect most of the electronics manufacturing to take place. But let's look at the current producers. We are a disruptive process. So the current producers are companies like Sumitomo, Sasol, South African company, Bukowski is French company, Hebei Pengda. Now these are chemical companies. So with chemical companies, they tend to buy their feedstock to produce a chemical. And the feedstock they use is actually aluminium metal powder. It's a very expensive feedstock. They dissolve it using alcohol and they hydrolyze it to make alumina. Now, remember I said they couldn't use the smelter-grade alumina because of the sodium. They have to use aluminium metal. So when you think about their process, it comes from the bauxite process. They make smelter-grade alumina. They send it to the alumina refineries, add a lot of electricity. These guys then dissolve it back down to alumina. So the question is, if you can come up with a process that bypasses the aluminium metal stage, would you be much cheaper? So this is what we've got. We have a process that we take it straight from the ore to the alumina in one single step. And the only reason we can do that is look at the colour of the ore body we start with. It's a kaolin deposit. Now, as you know, kaolin is used in paper manufacturing, used in ceramics to make things white, and it's got very low impurity levels. So a lot of the impurities have been leached out over millions of years, and we're using the alumina in the kaolin as our feedstock. So very low iron compared to bauxite. We have nearly 250 years of material in Meckering. We own this deposit, and we recently have got all our permitting ready for the construction. We chose the downstream process to Malaysia in a chemical park straight across the road from Singapore. And part of the reasons is operating costs. We want to be the lowest cost producer in the world. But more also, the Malaysian government gives us a 5 to 10 year tax-free incentive to build that plant there. So you know Dyson, the vacuum cleaner people, they've shifted all their operations from the UK to Malaysia because of those incentives. The process itself, we didn't come up with it. It's been around since the early 80s. It uses hydrochloric acid. It dissolves the alumina and it produces a product. So our business strategy is very simple. There are 4 bits of the puzzle. Basically, because of the new demand in the electronics area, we've got a high purity deposit, existing technology that's been around, and obviously experienced people. If you're chemically minded, this is the process. We take the material from Meckering, we screen out silica. This is the first part of the process. We use hydrochloric acid, we dissolve the alumina, we crystallize it out, and we have a purification, 3-step purification stage, and then we calcine it back to alumina. And in this process, we produce 4N quality alumina, 99.99%. The work started in 2011. We've done pilot plant work, we've done a BFS, and recently we've announced the final investment decision study. That's the plant we want to build, 4,500 tonnes per annum. Capital cost is $298 million US. The NPV, or the discounted cash flow, is $500 million US. Internal rate of return is 22%, and the payback at its full rate is just under 4 years. The net cash it generates at its full rate is around 76 million per annum, and we are targeting debt of 185 million from a German bank. So I'll talk about that in a second. Production cost is about just under $10, where our competitors are probably double that. And our long-term price in our financial model is about $27 a kilo. Okay? Today, the price is at $40 a kilo in Japan. And if we plug that into our model, the NPV is actually close to $500 million NPV. The IRR is about 33% on the current spot rate, and it generates an EBITDA of 133 million. We are half the cost of the conventional process. As I said, we're a disruptive process, and we have offtake with Mitsubishi. So all our product for the 10 years will be sold to Mitsubishi. And the reason they are involved in this is because they see the strategic nature of the material in the lithium battery sector as well as LEDs. As I mentioned, we are accessing debt of 185 million from a German bank called KfW, IPEX Bank. It happens to be owned by the German government, and of which 165 million is export credit finance. So what does that mean? We happen to have about 50% of our plant with German equipment, and we're accessing export credit finance. Now, the beauty of export credit finance is it's a long tenure, low interest rate, okay? So something like a 12-year loan with an interest rate of LIBOR plus 2.4%. So in Europe, LIBOR is about 1%, so something like an interest rate of 3.5% for 12 years. It's probably the best debt you can get around the world today, and that's why we took 12 months in due diligence with the bank. We expect a decision from the German government on the 14th of December, and that will be a catalyst for us. And then we'll be raising the project equity component next year, hopefully clearing the site in Q3, a 2-year construction period, and first product out by the end of 2020. Even our German contractor is an EPC contractor, is also a German contractor. Now, this is very interesting. We have negotiated with them where they will provide a fixed price, lump sum contract. They will guarantee the throughput, so the plant doesn't do 4,500 tonnes per annum, they will fix it. If the plant doesn't do the quality to meet Mitsubishi specifications, they will fix it, and they will guarantee the whole lot with a lot of performance bonds as well. Recently, we raised 17 million. SMS has further committed another 11 million to the project equity. All the consultants have completed the report, and we're now waiting for the final decision. On the growth of the company last 3 years, we like a steady growth. This is, we started at a market cap of 7 million. We're probably close to 55 million. And our share price is reflected in those 3-year period as well. So thank you very much.